In this video, I'm going to do one very detailed, thorough example introducing the concept of solving a trigonometric equation, a very basic one, and we're going to make use of inverse trig functions. And my approach to this may differ from some textbooks. I'm going to do this using reference angles because I think that's the most consistent, easy way to do it. Okay, so this may differ a little bit from other ways you've seen it. So the problem we're going to do is we're going to try to solve and list 6 specific solutions. Those are the instructions. And the equation we're going to try to solve is the sine of some angle x equals negative square root of 3 over 2. Okay, so we're trying to figure out what does x equal, right? What angles can x be so that the sine of that angle equals negative square root of 3 over 2? And just some initial observations, x can have an infinite number of solutions here because there are an infinite number of angles that are coterminal that could give you the same output from the sine function. So when we say solve, we mean find all solutions, all infinite solutions. So that in itself will be a challenge. So we'll have to learn some notation for that. And then once we have all the solutions, we can easily narrow it down to 6 specific solutions. So that'll be kind of our reasoning as we work through this. Okay, so the first thing I recommend is draw a picture of what's being described. And so if I'm determining the sine of some angle equals negative square root of 3 over 2, then that means x could have a reference triangle. Since sine is negative, our reference triangle is down, since sine measures up and down. So we're going to have a negative down measurement. So we have 2 possible reference triangles for this. And sine is opposite over hypotenuse. So one way to think of it is this side is negative square root of 3 over 2. Or sorry, that's one. You could do it that way. Let me go ahead and say that while I've got it. You could think of the opposite side, the vertical side, being negative square root of 3 over 2 and a hypotenuse of 1. And that would be the case over here as well, because the hypotenuse is always positive and the vertical side is down, so those would both be negative. And we could proceed to solve it from there. Okay, so that's perfectly okay. And that's actually pretty useful because then you should recognize this is a 30, 60, 90 triangle. And if you do, that's great. Okay, but oftentimes you won't have a nice ratio like square root of 3 over 2. So in that case, you might want to use your opposite side as negative square root of 3 and your hypotenuse as 2. And you'll get the same reference triangle, just the sizes will be different. So vertical negative square root of 3, hypotenuse 2, vertical negative square root of 3, hypotenuse 2. Now in this particular problem, we don't need to know the adjacent side because what we're trying to do is, what we're trying to do here is find all the angles that land on this terminal side and all the angles that land on this terminal side. Okay, so what would be useful here is to find the reference angle for x. Okay, so the reference angle, remember, is this angle right in here at the origin of your reference triangle. So we'll call this angle x bar. And notice that these 2 angles are the same for our reference triangle. In fact, if I drew my reference triangles up here, of course they'd be positive square root of 3 over 2 because they're up. The reference angle here is the same as well. So what I want you to understand is the reference angle is independent of quadrant, and more importantly, independent of the sines. So here, when I want to find x bar in any of these 4 triangles, it's going to be an inverse trig function of the 2 sides that I'm given of some kind. So in this case, our reference angle x bar is going to be, since I have the opposite and the hypotenuse, it's going to be the sine inverse, because it's opposite over hypotenuse, of the ratio opposite over hypotenuse. Now notice that when you find your reference angle, this is maybe the most important aspect of this introductory video, always use the positive ratio input when finding reference angles. Okay? Because reference angles are independent of the sines. Okay? It doesn't matter what quadrant you're in, it's still the same angle measurement. So in this case, if you plug that into your calculator, you should already know what this is, but if you don't, you'll see that it is, if you're in degree mode, you'll get 60 degrees, or if you're in radians mode, you should get pi over 3. Okay? Now, when you're solving trig equations, we usually give our angles in terms of radians. Okay, so we're going to use pi over 3. So let's reevaluate this picture with our new information. So we've got this new picture. This angle is pi over 3. And this angle, this reference angle, is also pi over 3. The question is, what is x? X is not the reference angle. X, remember, is measured from 0. Okay, so 0, the angle of 0, remember, is on the positive x-axis. So x, so if I start at 0 and rotate in the positive direction, the first value of x that I get would be that angle there. Well, notice that this rotation from 0 to here is pi, and then the rotation from here to here is another pi over 3. So x could be pi plus pi over 3. If you add those, you get 4 pi over 3. So that is one angle. That is one angle that lands right here. That's the first angle that lands there, as a matter of fact. But we know that there are many other angles that land there too. For example, if I do another full rotation, I'll land there again to get another coterminal angle. In fact, the way to get that is, in fact, let's call this guy x sub 1 because that's the first x value. But if I'm just talking about, let's look at x sub 2 then, the one I've got drawn here. It would be my previous angle, 4 pi over 3, plus an entire rotation, which is 2 pi. Okay? And I'm going to leave it like that so you can see what happens next. If I continue that pattern, then my next x value is going to be that 4 pi over 3, my starting point, plus 2 times 2 pi. So what you might start to see is you could call x sub 1 4 pi over 3 plus 0 times 2 pi because you're not adding any additional rotations. You could call 2 pi, you could say you're adding 1 times 2 pi. And if you keep going, you're just going to keep adding more 2 pi's. So what are we saying here? How can we describe this? There's a certain pattern here. In this pattern, this number is changing. Okay? It's called an integer. In fact, I could go backwards, and if I rotated backwards, I'd be subtracting 2 pi to get the same terminal side. So I could have, if I wanted, I could maybe, let's say, I should have labeled these differently, but the previous x value before this would be 4 pi over 3 minus 1 2 pi, and I could keep going and do minus 2 2 pi's, etc. Okay? But the point is, all of my answers for x that land right here are 4 pi over 3 plus some number k times 2 pi. And k is an integer. Now the way we write that, typically we write that as 4 pi over 3 plus, and then this portion we just multiply together and call it 2k pi. And fancy notation for k as an integer is we say k, and then we put this funny looking epsilon. It's like a lowercase c with a line right here. Epsilon, it means is an element of. So k is an element of the integers. So the integers are like a capital Z. You draw over and down and you stop, pick your pin up, come back here and you go down and over. So k is an element of the integers. So what that describes, if I zoom out now, that describes every single angle that lands there on that terminal side. But that's not all of the angles that make the equation true, because we also have to describe the angles that land right here, right? So we have to decide those guys. So let's draw another picture and focus on that for a moment. So if I'm looking at the angles that land here, keep in mind that our reference angle here was pi over 3, and this is 0. So the first x value that I get would be right here, stopping that terminal side. Well, in this case, I don't look at this rotation here, which is 3 pi over 2, and then add this portion, because this portion is not clear. I mean, we can figure it out pretty easily, but we don't want to have to do any work. So instead, what we're going to do is we're going to start by rotating all the way around back to the x-axis, which is a rotation of 2 pi. So that first x value is going to be 2 pi, but then I need to back up pi over 3. You use that reference angle pi over 3 that you found. Now 2 pi is the same thing as 6 pi over 3 minus 1 pi over 3, and that is 5 pi over 3. Okay, so our first angle here is 5 pi over 3. And just like before, now we can generalize pretty easily. All the angles that land here would be 5 pi over 3. X could be 5 pi over 3 plus an integer times 2 pi, which we write as 5 pi over 3 plus 2k pi, where k is an integer. Okay. Now, sorry, that's not going to work, is it? Now, just so you understand what the integers are, in case that's not clear, you don't remember from previous classes, integers are all the positive and negative whole numbers. Okay? So these negatives will be negative rotations, the 0 will be no rotation from that starting angle, and the positive numbers will be positive rotations from your starting angle. So the solution to this equation, there's an infinite number of those, is that x could be 4 pi over 3 plus 2k pi, or x could be 5 pi over 3 plus 2k pi, where k is an integer. Okay? Those are all the solutions. So it's kind of a creative way to list them all. You can plug in values of k to get specific solutions. So if I want six specific solutions, lots of ways to do this because there's an infinite number of them. You can do pretty much anything you want that satisfies these two equations. So kind of the standard practice is, well, let's start when k equals 0, because that's 0 is the most basic integer perhaps. So if k is 0, then we get x equals 4 pi over 3 plus 2 times 0 times pi, or x equals 5 pi over 3 plus 2 times 0 times pi. And so that means you get 4 pi over 3 for this guy, or you get 5 pi over 3 for this guy. So there are two solutions. We need 4 more. Let's now look at if k equals 1. If k equals 1, we're going to have 4 pi over 3 plus 2 times 1 times pi, which is 2 pi. Or we're going to have 5 pi over 3 plus 2 times 1 times pi. And so 4 pi over 3 plus 6 pi over 3 is 10 pi over 3. 5 pi over 3 plus 6 pi over 3 is 11 pi over 3. And there are 2 more solutions. And you might start to pick up on the pattern now. Every time you go up, you're going to add 6 pi over 3's. Notice that's incrementing by 2 pi. And this guy goes up by 6 pi over 3's. Okay? So you can plug in k equals 2 if you want, but I'll go ahead and tell you that if you add 6 pi over 3 again, you'll get 16 pi over 3. And over here you'll get 17 pi over 3. And there are 6 specific angles, 6 specific x values that make the sine of x equal negative square root of 3 over 2. You can plug in any of those angles and see that this is true. All right? So kind of a tricky topic. A really good application of inverse trig functions to find reference angles. And then once you've got your reference angle, you just have to use the quadrant to figure out how to write your actual angle. In this case, it was called x. Okay? Fancy notation here with k and the integers to make sure we hit all of the solutions. Good luck practicing.